Today we will discuss about a robot anatomy, the manipulator of an industrial robot. So manipulator here basically we are addressing autonomous manipulator. Okay, so the initial applications of industrial usage. Okay, so referencing from there. So that type of robot that is consisting of a series of joints and links. So different joints and links comprise the study of a robot anatomy as well as other aspects of the manipulator's physical construction. So a robot joint provides relative motion between two links of the robot. So each joint or axis provides a certain degree of freedom of motion. Yes, degree of freedom just we covered in the previous topic. Okay, so now continuing from the same topic here now. So in most cases, only one degree of freedom is associated with each joint. So so a robot complexity can be classified according to the total number of degrees of freedom they are possessing. So here in this diagram, we can see the joints and links in a robot. So here, the robot that is a stationary robot or a autonomous manipulator, it is attached to a base. That is why it is stationary. One end is fixed to the base. Then link 0, through that there is a joint 1. From joint 1, there is link 1 and then joint 2, means between two joints. Joint 1 and joint 2, there is a link 1. Then link 2 and joint 3. So between joint 2 and joint 3, there is link 2. After that, from joint 3, there is link 3 and then the end of the arm. Here we will be connecting the end effector or the tool. So now comparing with the human arm, joint like the shoulder joint, elbow joint, wrist joint. Okay, then the link that is the arm between the shoulder joint and the elbow joint. Okay, forearm. Okay, the section of the human arm between wrist joint and the elbow joint. They are the links. Okay, so each joint is connected to two links, an input link and an output link. So with the joint providing controlled relative movement between the input link and output link. So a robot link is the rigid component of the robot manipulator. So rigid, it has to be very strong. Then most robots are mounted upon a stationary base such as the floor. Not necessarily the floor, but commonly we can call it. From this base, a joint link, okay, that is started. So this is being indicated in the figure. So the robot base and its connection to the first joint, that is link 0. Then first joint in the sequence, that is joint 1, link 0. Therefore, the input link for joint 1, while the output link from joint 1, that is link 1, which leads to joint 2. So another joint. Between two joints, there is a link. One is the input, one is the output. So thus link 1 is simultaneously the output link for joint 1 and the input link for joint 2. Okay, then this joint link numbering scheme follows the same fashion for all joints and links in the robot system. Now coming to the types of joints. So linear joint, orthogonal joint, rotational joint, twisting joint, and revolving joint. Now let us cover each of them briefly. So the linear joint or the type L joint. Linear, it means only linear movement. Like in the diagram it is shown, only the output link can move only left or right. So in or out. Okay, so the relative movement between the input link and the output link is a translational sliding motion. Okay, here in this case, it is only left, right. With the axis of the two links, they are parallel. Okay, axis that will be parallel. Another type, that is the orthogonal joint or the T joint. So here the relative movement between the input link and the output link is a translational sliding motion. Yes, here also left and right. The output link can move only in these two directions, so translational type of motion. But the axis of the output link that is perpendicular to the input link. So output link and input link, their axis, they are at 90 degree. Next, joint that is a rotational joint. So this type of joint that provides rotational relative motion with axis of the rotation perpendicular to the axis of input and output links. Okay, so axis of both of them, they are perpendicular and we are having a rotational motion in this type of joint. Then twisting joint. Okay, twisting, like the screw. The output link. So this is the twisting joint. It provides rotary motion, but the axis of the rotation is parallel to the axis of the two links. Okay, means the output link can twist clockwise, anti-clockwise. Okay, it will not rotate, it will only twist. So next is revolving joint, a type V joint. So the axis of the input link is parallel to the axis of the rotation of the joint, and the axis of the output link is perpendicular to the axis of rotation. Okay, means it will be having a revolving type of movement. So here it is shown in the diagram. A rotational type of motion is there, but the axis of both of them, they are perpendicular. Okay, so a brief description. So linear joint, the relative movement between the input link and the output link is a translational sliding motion with the axis of the two links that is parallel. Then orthogonal joint, the relative movement between the input and the output link is translational, but the output link is perpendicular to the input. In rotational type of joint, the movement that is rotational and the axis that is perpendicular. The rotation perpendicular to the axis of the input and the output link. Then twisting joint, it is also providing a rotary motion, but the axis of the rotation that is parallel to the axis of the two links. So this is the difference between the rotational and the twisting joint. Both are providing rotary motion, but in case of the twisting joint, the axis of rotation that is parallel to the axis of the two link, whereas in case of rotational joint, the axis of the rotation that is perpendicular to the axis of the input and output link. The last one is the revolving joint. So the axis of the input link is parallel to the axis of the rotation of the joint, and the axis of the output link is perpendicular to the axis of the rotation. Means this is rotating with the output link at 90 degrees from the input link. Okay, now the last joint there, that is the wrist assembly. So robot wrist assembly consists of either 2 or 3 degrees of freedom, because this is similar to the fingers, the wrist joint and the fingers attached there. So the end effector in the robot that is attached here to the wrist assembly. So the base here, the dark blue colored base, that is attached to the robot arm. Then first joint or the first axis, then second axis, the third axis. So three axes are there. So each one of them can give a revolving type of motion. So a typical 3 degree of freedom wrist joint that is being shown here in this figure. So the roll joint is accomplished by use of a T joint. Okay, here we are using or seeing the application of a T joint. The first rolling joint that is accomplished by the use of T joint, then pitch joint. Okay, the pitch, yeah, the first one attached to the base. Okay, that one is achieved by R joint. Okay, then the yaw joint, a right and left motion is gained by deploying a second R joint. Okay, let us go back and see the type of R joint here. This one, the rotational joint. Okay, now robot workspace. The work volume or work envelope, that is a three-dimensional space in which the robot can manipulate the end of its wrist. Means in this space, it can do any type of useful work. It can move here freely. Okay, then robot work envelope, that means the envelope of all points which can be reached by tip of the robot. Okay, so that is the maximum reach of the robot. That is the envelope. So work volume is determined by the number and type of joints in the manipulator, the ranges of the various joints, and the physical size of the links. The work envelope, that is its actual shape, is depending on the robot's configuration. How many joints are there? The dimension of the links, type of joints, number of joints, size of the links. Okay, so these factors. So a polar robotic configuration tends to produce a spherical or nearly spherical work volume. Then cylindrical configuration has a cylindrical work envelope, and a Cartesian coordinate robot produces a rectangular work envelope. So here are the diagram. So it is a first case, that is a rectangular prism for Cartesian robot. Okay, then the second diagram, the movement that is round. So a section of cylinder for a cylindrical robot. Front view and the top view. Okay, so for spherical polar robot, for articulated robot, here we can see How it is moving? Side view and the top view. So here we can see different type of work envelopes which we just studied. Cartesian, cylindrical, spherical, articulated. So in this type of shape or the 3D or the space, this type of space, it can move or do some type of useful work.